I described a mathematical basis for the moment distribution method in lecture SA 37. In lecture SA 38, we examined the use of the method for analyzing continuous beams with pin and roller supports. In this lecture, I'm going to explain how to handle fixed supports. Let's consider the continuous beam that we saw in the previous lectures, a beam with one pin and two roller supports. From lecture SA 38, we know the distribution factors for the joints. They are if you recall, we said that since there is only one member connected to the pin support, the distribution factor at A is 1. That is, any bending moment present at A is going to be distributed to the left end of AB in its entirety. But what if there is a fixed support at A? Would the distribution factor still be 1, since there is only one member connected to the joint? Common sense suggests that different support types should lead to different distribution factors. To investigate this and to better understand how the two factors differ, let's adopt the approach we used for determining the distribution factors for joint B. In lecture SA 38, we saw how the distribution factors at B can be calculated using the member stiffness coefficients. Each member has a stiffness coefficient equal to its EI over L. The total stiffness at the joint equals to the sum of the coefficients for the members connected to the joint. The distribution factors at each joint are calculated by dividing the coefficient for each member by the sum of the coefficients. To apply this approach to an end joint of a structure, we define an imaginary member attached to the other side of the joint, like this. We then assign a stiffness coefficient to that imaginary member. For a pin connection, the imaginary member has a stiffness coefficient of 0. That is, there is nothing to the left of A that would contribute to the overall stiffness of the joint. We could say the member has a modulus of elasticity of 0. For a fixed support, like a rigid wall, the stiffness is assumed to be very large, large enough to prevent any movement of the structure at that joint. Therefore, we could assume a stiffness coefficient of infinity for our imaginary member. Therefore, for a pin support, the distribution coefficients can be computed like this. For a fixed support, the distribution factors are when writing the moment distribution table, we don't write this distribution factor at A since it does not play any role in our calculations. But when the support is fixed, we can write both distribution factors since they enable us to determine the moment reaction at A, as well as the left member end moment for AB. Let's see how the moment distribution process works for a continuous beam with a fixed support. Consider this beam. Here are the distribution factors for the joints. Note that here the table has one additional column, the very first column. This column gives us the moment at the right end of the imaginary element. The second through fifth columns are for determining the end moment for real members. From lecture SA 38, we know that the fixed end moments for member AB are: we start by balancing joints A and B. At A, we multiply -4 by 0 to get the moment value for the right column. We multiply -4 by 1 to determine the moment value for the left column. Note that now joint A is balanced since sum of the moments at the joint is 0. To balance joint B, we multiply 4 by 3/5 to get the moment value for the left column, and we multiply 4 by 2/5 to determine the moment value for the right column. Now we carry over half of 2.4 to the other side of member AB and half of 1.6 to the other side of member BC. But there is no need to carry over half of -4 to the other side of our imaginary member, since it is not a part of the real structure. Again, we balance joints A and C. Then we carry over half of the balancing moment at C to the other side of member BC. It is time to balance joint B again. Then we carry over half of each balancing moment. After a few more iterations, the moment values become negligible, signaling the end of the process. We then add up the values in each column to determine the member end moments. Now it is time to calculate the member end shear forces by applying the equilibrium equations to each segment, like this. Finally, we determine the support reactions. Here are the reactions for the beam.